Good morning. I'm Alejandro Sánchez de Miguel. I'm currently working at the University of Exeter, but many of my colleagues are either in the Complutense University, where I made my PhD, the DSLR of 𝗖𝗀, and obviously some people that collaborate with us from NASA and the European Space Agency. And this is work that I hope you will be able to see very soon, as the paper is under review. The first thing, everybody knows this image. The only problem of this image is that it's fake. Yeah, these colors are not real, and the real image here, I don't need to explain it that much, is this one. No, and why this is important? Why this image and not the other one is the real one? Well, the problem is that, well, we are trying, and hopefully soon we'll be able to release a real color map of Europe using ISS images. But why is so important to have a map of the Earth at night? Well, is to have an accurate measurement of the light emission. And what is the problem with the color? Well, one of the big problems that we have is the current transition that Chris already mentioned from high-pressure sodium lamps to LEDs. For example, in one work that we published 2 years ago, you can see more details in the article. For example, we studied what happened in the city of Milan, this with images of the ISS, and to see it in a different way, if you see those two images, the change is not very clear. Maybe the right one is a bit more lit. But when you have the color information, you have much more information. You really, the change is much more dramatic. And now the intensity change is not so clear. When we see what happened with the beers inspecting Milan, we see that Milan had a decrease on beers over 50%. That was real or was not? No. The thing is that if we compare with what our eye should see if we were in Milan before and after, we don't see any change. And the reason is because the municipality of Milan changed the illumination to match the same photopic vision before and after. But the beers don't see that and produce a problem. No? If we consider the photopic intensity, yeah. But if we consider the blue light that is linked with many environmental issues or health, there was a 27% of increase on blue light. So it's a problem, no? One of the things is that beers is sensitive to infrared light that humans don't see, that don't produce light pollution, and indeed, many cases it's a kind of noise for us, depending on what's your goal, no, your target. The blue light, in other hands, humans see that blue light, cars produce light pollution, produce environmental impacts, and produce impacts on human health. And in more detail, this is the spectral responses of the beers, DMSP, and SQM. SQM is Square Quality Meter. And we see here the DMSP and the beers. Here they are the ISS. These are the two areas that we should think about. And we should not care only about the blue peak. Also, we should care about the high-pressure sodium lamps have a heavy emission in the infrared that the other kind of lights don't have. So, for example, when we change from high-pressure sodium lamps to LEDs, even if the photopic part don't change, that would be something like the green area, yeah, something between the green and the red area, the infrared and the blue change dramatically and produce these problems. Well, we presented all this in this paper, where we released many other things, like how you can classify and predict where the spectra of streetlights can be seen, how to produce photopic vision maps with the ISS images, and even create other indicators. But one of the things, for example, is in this paper is only using two channels, but we also did another paper that not so many people know, is using the 3 colors. No? With the 3 colors, we get even more accurate information for the human eye. This work, no? The calibration, no? Because this was a work made mainly using relative calibration, no? So now we are presenting the steps that we are preparing for the radiometric calibration of the ISS images using stars to get the absolute calibration. It's true that we have some issues in terms of sometimes the pictures are not taken from the same window, so there is some corrections that probably will need to be fixed later on in making an intercalibration, but we fix many of the issues that the ISS images has. For example, we fix the non-linear regime of the ISS. This is an example of a very wide 24 millimeter image from that you can see in the center Madrid, and on the edge you can see the Netherlands. It's very important that the people try to use the raw images of the ISS and not the JPEG, because the JPEG have first is a loose compression, and then also many times there's areas that are saturated in color and you are losing a lot of information. For example, on these topics that I'm commenting on the LEDs, no? And here you can see how in the bottom part in the JPEG nearly you cannot distinguish any colors, but when the same image is adjusted using the raw, you really can see how there's huge differences between different areas. This is the area of Madrid. But what happened that dealing with the raw image is not that simple. In reality, is 4 images embedded in one. So what we do is we extract all the information in 4 images, green, red, 2 green images and a blue one. Then also we consider how the image is deformed to using geometrical transformation, elementary geometrical transformations, to infer where was truly the nadir where the ISS was taking the picture, because the time that the ISS gives to the pictures is not the real time, is the time of the camera, and a small the offset of seconds can mean hundreds of kilometers. No? That's why it's quite difficult to find high resolution images. For example, we can have up to 5 meters per pixel with the ISS, as Chris saw in his presentation. But many times it's difficult to find because they are not in the area that you are trying to find them. We also correct from the flat field or vignetting. This is a correction that honestly anyone using an ISS image should do, no? Because you can see, for example, here how there is a huge difference between using an ISS image that you have your subject in the center of the image or in the edge. We try to buy all the lenses that are using the ISS to be able to correct all this effect. Here is calibrated, it's not a stretch, but so you see more or less the values that we get, the units, and this is geo-corrected. You can see how effectively we can correct the deformation of the image and get a huge area. Obviously, the the resolution in the area more close to the nadir is higher than the resolution that we have farther away. We also, as we know the location of the true nadir, we can also calculate what is the angular distance in the image and make an atmospheric correction. Here, this is the already calibrated image of Madrid, well, of the image that I showed you before. But one of the issues, as I said, is the intercalibration, no? Because many times we want to compare with other images taken in similar area. We can have issues like the moon, or well, just that the images are taken in different windows and we want to use a common reference. So, for example, what we did here is take the output of our algorithm and make an intercalibration with BIRS. No? In this case, is not very high resolution ISS image because we are using a 24 millimeter image that is very, very wide. But this is the area of Madrid. And for example, you can see how, as this image is taken much earlier in the evening, you can see how the center of Madrid, the financial center, is lit. Although here, for example, the only thing lit in the center is the Santiago Bernabeu football stadium. So with this, we can fix the problem of acquisition. And this is the comparison, no, between the images. This is the density plot that we use to create the intercalibration, no? And the intercalibration fits nearly perfect with a one-to-one line that is the red line. We don't trust these dates, okay? I put it a bit approximately, but this allows us to make intercalibrations between, for a specific city, like can be in this case Barcelona, and see how specific place, like can be the Zona Franca, the port, is changing in color. Also, we have to consider that we have ISS images since 2001. Not many, I have to say. Most of the images that we have are since 2012, but some even we have quite early. And the range of resolution that ISS can produce is from 5 meters, not many images, but in very relevant places, up to 200. No? And many times we have time lapses, so that covers a huge area that we can process. Here is an example, so you can compare BIRS, LIWA, ISS, and daylight. This composite was done by 𝗖ญ่his𝗁. And in these ISS images, we can see things that we cannot see other way. No? For example, the difference of color between East and West Germany, the border between Mexico and the US, the color change in the north, and this is all. Just one last thing. If you want to get these images calibrated, how you can get them? Well, you can collaborate with a project, citiesatnight.org. You also can hire a spin-off company from the project that more or less, many times we can make better deals, but the price usually is 1,000 euros per image. And also you can wait that we make the data release from the mission project. That is where I'm working right now. That will be a lot of images for everybody, but mainly for Europe. And if you have any questions, obviously, also you could hire me.